literatures or some of the available. So what is shown here as frequency reconfigurability and what is shown here as pattern reconfigurability. See, out of interest, I just wanted to mention like what are the methods for pattern bandwidth reconfigurability. This is for if you wanted to go for a frequency reconfigurability, as I said, so we can tune the electrical length by pin diodes, and we can use varactor diodes, and we can use matching networks as well, and we can go for additional shorting post or etc. So these are the methods. And similarly, for if you want to, you can see clearly here, this is tuning of frequency, and this is tuning of bandwidth. Each response is different in its bandwidth. The bandwidth is between, there can be 6 dB bandwidth or 10 dB bandwidth. So normally in circuits what we see as 3 dB bandwidth, but for antenna we would say it is 6 dB bandwidth or 10 dB bandwidth. And this is bandwidth, it is sourced from IEEE. So some of the publications which is already done. So this antennas also you can see, these are all minimal sized antennas and compact antennas. So here between this meander lines they have put the pin diodes, and here also they are using pin diodes for pattern reconfigurability by changing the electrical length exactly. And these antennas are polarization and radiation pattern. So what you see here is the polarization reconfigurable antenna, and what you see here as what you see here as pattern reconfigurable antenna, and what you see here as polarization reconfigurable antennas. So again, like we're employing modified structures like slit, parasitic patches, etc. So those are the standard methods which people use or which researchers use for reconfigurability. Okay. And now coming to the problem, like we identified the frequency, like we trialed multiple antennas. With a trial of multiple antennas of 2.4, 5.8, 915, 415 different antennas, and thus 915 megahertz is identified. So this initially we tried for a 5.8 gigahertz antenna, and as you know, I don't have to explain about this. Those who are into the antenna design might have known these. These are the standard design formula for antenna design. So one shot, this slide gives the entire design formula for antenna design. So you can see the width of the pass, length of the pass, normalized length. So there is effective permittivity. So this we will put it here, and that is how we find the length, and then substrates, feed length, wavelength, feed path. There are different feeds also. So thinking that first lecture is for you as on the fundamentals, I'm not moving on like feed length or feeding or direction, what is radiation pattern, etc. I'm not moving into that. So now, so we have gone for this antenna. This antennas we have designed, it is antenna arrays. We may not call this as antenna. This is antenna array. Why do we go for this arrays? Initially, we wanted to test which frequency can be utilized. So we went for multiple designs. So as you know, this is this antenna is an antenna array, and it was giving us higher gains also. You can see up to 8. So we tested with this, and this is nothing but the phase simulation, reflection coefficient of the antenna, and the pattern, directional pattern of the antenna, because we want 2.4 and omnidirectional is not an issue. The issue here is directional antenna which can transmit the 1 meter thickness hermetite concrete wall. So we went for the directional antennas. So the measurement results, and also like the parameters, as you see, these parameters are below 10 dB. So antenna is transmitting, and then the gain of the antenna you see here. So up to 11 dBi. So up to 11 dBi gain we designed using number of arrays. It is not a single antenna, using number of arrays and as well as directional. However, since we increase the gain of the antenna, there is a trade-off between gain and the radiation pattern, radiation efficiency. So you can see the efficiency of the antenna is compromised here since we increased the gain, and we went for a 915. So it is not like suddenly after 5.8 we went for 915. We decided. So we tested with several antennas, and several commercial antennas are also we tested. Then we went for 915, And through this 915 antenna, like we could get a better reflection coefficient, gain, directivity. You can see higher directivity for the array, and then since our directivity and gain is higher, the efficiency is less. Okay, we just wanted to check whether this frequency can be utilized or not. So now with this antennas, we tested at the WSN. So the testing was performed inside the WSN lab. We tested it SSN as well. It was performed inside the WSN lab, and we generated or we designed a transmitter for this. So as I said, this 915 is not an available frequency. So we do not have a 868 or above 900. Those frequencies are not licensed in India. So we do not have a transmitter. So we developed a programmable transceiver which can, so that we can, that is not a part of the work, but that is created for testing the antenna. Only then we can test it. If there is no modem to test the 915, then we cannot test it. So we developed it. So, it is not very difficult to create a transceiver or transmitter or receiver. We use the modules which are available. So like if we wanted to go for 915, that is 150 to, that will go for 150 to 960 power amplifiers. We were getting data with additional, so the transmitted power we increased. So inside the nuclear reactor, so in the RCB also, with this antenna we did not receive. With this antenna, even with it is not receiving, and 915 we started receiving packets. For 5.8 we did not receive it, and for 9, so these packets started receiving. So that's how we decided this 915 megahertz antenna would do. But however, it is additionally using additional power amplifiers. But we did some, because since we are doing it now, like we tried with the substrate analysis for different thickness of the substrates and different thickness of different parts, thickness, frequency, etc. A lot of studies have been performed on this. So let me go to the point. So Roger also we tested. So these are, and it is easy to see that switching can be performed using this diodes, that diodes, etc. But if you wanted to design the switching circuits, it's really difficult. That biasing circuits will also degrade the performance of the antenna. When you have the switching circuits, which will degrade the performance of the antenna. So we went for RLC circuit, so usually RLC circuits are used. So we started using RC circuit because inductance is really a matter, and which is bigger in size in the circuit board. So we removed that and we used only RC circuits for the switching. So this is our switching configuration. So we used switching circuit in the top radiating patch, and this is our switching circuit in the bottom radiating patch. So top and bottom radiating patches, we went for two different types of switching circuits. And so we have this is our bottom patch, and top patch, it is connected in this way. So where in between we gave RF excitation. Now let me come to the point. So our original antenna design starts from here. So we started antenna design here, and this is the proposed design. It is not a very new design. You might have heard about this Alfred loop antenna. This is one kind of Alfred loop antenna because we wanted to cover all the frequencies. Listen, if you are placing a wireless sensor network, if you are placing a WSN at this place, let's say at this place, you have to cover all this area. You may skip at the back side of this. It is not 360 degree. But however, nearby this, you can leave it. The remaining areas, it has to entirely cover. So no antennas can be exactly omnidirectional. It is like omnidirectional. That's it. So that's how we took it. So this is our first quarter section of the proposed antenna. So from this quarter section, it has been, this is the quarter top layer, bottom layer, and this is the antenna which has all the four sides. So this is 4 quarter sections on the top and 4 quarter sections at the bottom. And these are the dimensions of the antenna. So when you see, this is the, including this This is designed particularly for 2.45 gigahertz. But we want an antenna which will give us 2.45 as well as 915. So initially we tested for 2.45. So as you see, it exactly resonates at 2.45 gigahertz, and the standing wave ratio also measured. It is also within the limits. And then we have tested for the radiation pattern. So the far field radiation patterns, which was also fine. So the characteristics, so like you can see, the directivity is actually 1.4 and the gain is 1.4. The gain is not up to the level of what we require. This gain definitely below 2 dB cannot transmit through the wall. So we started improving it with additional